Hi there, my name is Charlie Farrior. Welcome to a little presentation I like to call Overexplaining the Joke, an analysis of vintage comedy routine. In this presentation, I'll be going over a variant of Mathemagic with a few examples. I will reenact a joke from 1935, and I will go in depth on why it works and how to make it work for other numbers. But first, what do we mean by a variant of Mathemagic? Well, up until this point, all the examples of Mathemagic that we've covered have been meticulously planned by a mathematician to result in them being able to predict the end product after a series of calculations. And this variant of Mathemagic isn't that different. The only quirk is that you are purposefully doing math incorrectly and hoping the other person doesn't catch it, which is a little something I like to call
dark Mathemagic, where you prey on the innocence of your fellow man and let them assume that everything you're saying makes complete mathematical sense, when you know that in reality it makes no sense. It's complete mathematical gibberish, but they don't know that, and all of a sudden everything they believed in was wrong.
Anyways, let's look at an example or two. Right here, we have a square of side length 21 centimeters and an area of 441 square centimeters. If we divide it up into sections with side lengths of 13 and 8, corresponding to Fibonacci numbers, we can reassemble it into this rectangle of side lengths 13 by 34. However, 34 times 13 is 442 square centimeters. I created a little bit of extra area out of nothing at all. It's magic! Except it's a lot less actual something from nothing and a lot more slipping an extra card in the deck. If you look at the angles alpha and beta and do some simple arctangents, you can see that the angles are not quite the same, meaning that there's a very, very, very small 1 square centimeter area having parallelogram where this red line should be. They just seem very, very close due to the nature of the golden ratio. Or there's this little trick where you forget that the associative law of addition breaks down an infinite series. So 0 is equal to an infinite sum of zeros, which is equal to an infinite sum of 1 minus 1s, which is equal to 1 plus an infinite sum of negative 1 plus 1s, or 1 plus an infinite number of zeros, or 1. All of a sudden you create something from nothing. And those are all very fun. But there's a very particular math joke that was popularized by Abbott and Costello in 1935 that I'm very, very fond of, which is simply titled 7 times 13 equals 28. Now, it's pretty clear that this is the wrong answer, but it's going to be fun anyway. Now, instead of just showing you a 5-minute comedy clip from the 1930s and 40s, I'm going to have to reenact it for you. So, let's have some fun. Hey, this ain't nearly enough to cover 13 weeks of rent. What's the big deal? What the heck are you talking about? 13 weeks, $7 a week, that's still $28. I just gave it all right there. 7 goes into 28 13 times. If you can prove that to me, you get the room for free. But if you can't prove that, I want double the real value. 7 goes into 28 13 times? You know what? I'll prove it. You got a marker? Nah, never mind. I got one. All right, let's do this, right? 7 into 28. 7 to 2? 7 doesn't go into 2. Does 7 go into 8? Right, one time. Let's carry the 7. Now, 7 from 28 is 21. 7 goes into 21 3 times. Put that there. That means 7 goes into 28 13 times. No. Must be something else. You know what? Multiply it. Multiply 13 by 7. Dare you to make it 28. What? Alrighty then, fine. You know what? 13 times 7. Let's do this. 13 times 7. Alright. What's 3 times 7? 21. Right? What's 7 times 1? 7. What's 21 plus 7? 28. 7 times 13 is 28. No. There must be some sort of... You know what? All or nothing. Foolproof method. Add it up. 7 13s on the board right now. What? Oh my God, drumming up the wall. All right, fine. Let's do this. 1, 2, 3, 4, 5, 6, 7. Okay, I'll add them up for you. Nah. I'm adding them up, all right? I'll do it right. 3, 6, 9, 12, 15, 18, 21. 22, 23, 24, 25, 26, 27, 28. What? Here. Well, thank you very much. Teaching you to take your math classes a bit more seriously now. Hey. Oh, by the way, can you do me one quick favor? Can I exchange this 5 for 2 10s? And then I proceed to reenact every Abbott and Costello routine for another 3 hours. Okay, we should probably get back to the presentation now, right? But look, this was a lot of fun to do. And I had to work it out and do it with only one person doing a comedy duo act. So, you know. But anyways, let's get back to it and start analyzing exactly why this problem works and how we can replicate it with other numbers. All right? Cool. So, now let's take a quick look at the second and third methods of this calculation first, because they're the easiest to sort of understand where it went wrong. So, for the multiplication step, it's 13 times 7, 3 times 7 is 21, 7 times 1 is 7, add them up, 28, right? Except what's actually going on is I'm just adding 7 times 3 and 7 times 1 to get 7 times 1 plus 3, or 7 times 4, right? I'm just adding up all the digits in the addition step, right? 7 3s, 7 1s, so it's 7 times 3 plus 7 times 1, 7 times 1 plus 3, or 7 times 4. So all I'm really doing is just adding up all the digits or multiplying 7 by the sum of the digits of 13 to get 28. Now, this could work for pretty much any numbers. You can just multiply the second number to every digit of the first one, add them up, and get the end result. However, it's the first step that's a bit more complicated and sort of where the beauty of this trick comes into play. So let's take a look. Now, for the first part of the trick, things get a little bit more complicated. We're going to need to start generalizing. So instead of just writing down 7 goes into 28 13 times, we're going to do it with A, B, and C. Meaning we're going to have A here divides into C, B times, right? And let's go ahead and start separating these out into digits, right? So we know that B and C are 2-digit numbers, meaning that B is equal to B1 plus B2, 10 times B1 plus B2, C is equal to 10 times C1 plus C2, and we know that A, B1, B2, C1, and C2 are all single-digit numbers, right? Now, what we learned with the second and third parts of the trick was that 7 times 13 doesn't equal 28, it's 7 times 4, or 1 plus 3. Meaning, the first thing we know for certain is that A times B1 plus B2 is equal to C. Correct? Because that's the calculation we've been making all these different times. And it's true here as well. Which means that it's equal to 1 plus 3, and here it's equal to B1 plus B2. Also, let's go ahead and eliminate 0 from any of these possible digits, because if we say that A is equal to 0, we can't divide it in the first place. If B1 or C1 are equal to 0, then these aren't 2-digit numbers. If B2 is equal to 0, that means that this number here would be 0, which means that this would have been eliminated in its entirety, which wouldn't be possible given how we do this trick. And we say that C2 is equal to 0, then we can't subtract anything from it anywhere. So we can go ahead and eliminate that possibility entirely. Now let's go step by step to the trick. First thing I ask is, does 7 go into 2? And we say no, which means that we know that A has to be greater than C1. And then I ask, does 7 go into 8? And we say yes, which means that A has to be less than C2, second digit of the number. So we already know for certain that A times the sum of B1 and B2 has to equal 3, equal C, and A has to be in between the first and second digits of the number. And this will actually help narrow it down extremely once I show a little bit more pieces of the inequalities. Now let's start working on some general formulas based off the ones we already have. First off, let's work with C1 is less than A. Now, since all the digits we're working with so far are natural numbers, that means that C1 is less than or equal to A minus 1. And we multiply both sides by 10. 10 times C1 is less than or equal to 10 times A minus 10. Add C2 to both sides. We can say that 10 times A minus 10 plus C2 is less than 10 times A minus 10 plus 10 because C2 is less than 10. 10 times C1 plus C2 is equal to C, which means C is less than 10A minus 10 plus 10, or C is less than 10A. Next, we take the information that C1 is less than A, but C1 is also greater than 0, which means that A can't equal 1, because if it did, then C1 isn't 0 and isn't 1, so it wouldn't exist. And by a similar bit of logic, if A is less than C2, which is less than 10, then A can't equal 9. So these are both critical information on what A can be. And last but not least, probably the easiest one to derive, is that because A times B1 plus B2 is equal to C, A divides C. So all in all, what are we looking for? We're looking for a multiple of C, or a multiple of A, which is less than 10 times A, and we know that A has to be a number that's from the set 2 to 8 inclusive. And we need to make sure that C1 does not equal 0, easy enough, and that C2 does not equal 0. Alright, now we know the rules. Let's start looking for numbers. So, first things first, I listed out every possible multiple of A, given the numbers that we know A can be from 2 to 8, and made sure that they didn't reach 10 times A, which means that these two bits are now handled. Next, we know that the first digit of C cannot equal 0, which means no single digit numbers, which means all these are out, these are out, these are out, and these are all out. Next, we need to know that the second digit of C can't be 0. So that means we're going to eliminate a lot of multiples of 5. There we go. And that's that one handled. C1 less than A, we already know, since C is less than 10A, so we don't need to check that. So now the last thing we need to check is if C2, the second digit of C, is greater than A. So let's start with A is 2. 12, 14, 16, 18, all of them, their last digit, with the exception of this one, is greater than 2. Next, which digits are greater than 3? 2, not greater than 3. 5, 8, yes. This one, no. Those two, yes. Now 4. 12, no. With 6, yes. 4, no. 8, yes. 2, no. 6, yes. With 5, the 5 got messed up because either it ends in 0 or it ends in 5, which means no multiples of 5 will work for this trick. Now with 6, 2, 6, yes. 24, no. 36, no. 2, no. 8, yes. And 54, no. With number 7, 24, no. 14, no. 21, no. 28, this is the one that we've actually been working with the whole time. 35, not going to happen. 42, no. 49, yes. 56, no. That, and no. And then with 8, this one also got messed up because the maximum last digit value for a multiple of 8 is 8, which means you can never get a digit larger than 8, which means none of these work out. So we're only left with a few sets of numbers that this whole trick works with. There's that one, and there's that one, and there we go. Alrighty then, now I'll list this out in a more approachable way. But thanks to this sieve method, we've derived every possible pair of numbers such that this trick works. Okay, I've taken our 14 pairs of numbers that we've derived from our sieve method and spread them out and calculated the B values. If you don't recall how to calculate the B values, let's go ahead and go through the trick with one triplet of numbers. So, how many times does 3 go into 2? Doesn't. How many times does 3 go into 4? Once, so we write down a 1. 24 minus 3 times 1 is 21. How many times does 3 go into 21? 7 times, so we write down a 7. So that's how we derived every single one of these numbers with these 14 pairs, with this one being the Abbott and Costello one that we started with. Based off of all of our criteria for what we wanted for these tricks, we've come up with these 14 triplets of numbers. So if you want to mystify your non-mathematically inclined friends, go ahead, grab a set, and go through the whole routine. Have some fun. Now, if you want to get even more restricted, you can say, oh, I want to make sure that A and B are less than C, so this one doesn't work, or this one doesn't work. This one, 3 times 27 equals 27, that's too weird, I don't want to do that. Then you can go ahead and restrict down even further. But as far as I'm concerned, all of these are worthy triplets of numbers to test out this trick on. So I hope you enjoyed this little deep dive into dark mathemagic. And go ahead and do me a favor. Have a good day.